Hi guys, let's solve today's Leetcode problem, which is problem number 33, search in rotated sorted array. Okay, it's a medium problem. There is an integer array nums sorted in ascending order with distinct values. Okay, prior to being passed to your function nums is possibly left rotated at an unknown index k. Okay, such that the resulting array is something like this. For example, if this might be the left rotated array by 3 times. So this is the original array, and if we left rotate this by 3 times, it would become like this. Okay, so basically the first value comes to the last, and then so on. So like that, these three values came to the last. Okay, so we rotate the elements from the left side to here. Okay. Given the array nums, after the possible rotation and an integer target, return the index of target if it is in nums or -1 if it is not in nums. Okay, you must write an algorithm with O of log n runtime complexity. Okay, so this is the approach. We are given a rotated sorted array, and we are given a target. Now we have to find this target if it exists in this nums or not. If it exists, then we have to return the index. If not, then we have to return the -1. Okay, so that is the problem. Now if we see the constraint, so num's length is 5000 only, not very much. And important thing is that all the values of nums are unique. Okay, because we have solved a similar problem. I'll attach the video link in the description. So there, if the numbers given are not unique, means there are duplicates. So we need to handle duplicates differently. Okay, basically that was a finding minimum in a rotated sorted array, and in case of duplicates, we were not able to decide which side to go. So on such cases where we cannot decide due to duplicates, we have to explore both the sides, right? So for that reason, this is the important case over here, that all nums are unique, so we don't need to worry about the duplicates here. Okay, now nums is an ascending array, possibly rotated. Okay, we are going to cover two approaches. One is the linear approach and the binary search approach. Now let's check this. So in linear search, we are given this array, we have given this target, we have to just start our iteration. Our I will move from here and it will go till end. It will check for every value if it is equal to target or not, until it finds it. So in this case, it finds it, so it will return answer to be 4. Okay, the index that we have to return. If after iterating till all the indexes, let's say it reached somewhere here, if target would have been, let's say 10, it reached here, it didn't find the value at all, so at the end it can return -1. So, okay, so the same, this is the simple straightforward thing. So n is nums dot size. We are iterating over this nums, and if any time nums of I is equal to target, which means we have found our value, so we would return that index I. If after iterating over all the array values, if we didn't find it, then we have, at the end we have to return -1. So time complexity for this approach is O of n, since we are going over all the values of nums, and space complexity is O of 1 because we are not taking anything additional space. Okay, so that is the linear search approach, but problem itself says that, write the binary search. Though this approach will work, but we must know binary search approach to solve this problem. And how will we know that this problem is going to be solved by binary search? Because array is sorted. Okay, that is the key word to notice. Whenever it is sorted, we can definitely apply binary search. Okay, and then it is rotated. So since it is then rotated, then we have to apply certain things, but for sure it is sorted, so we can apply binary search. Okay, now what is the key intuition over here? That since the array is rotated and the sorted, which means one half of the array will always be sorted. Now, if you see this array is basically rotated and then sorted, right? Now, if I see that, let's say if I take, if I divide the halves, something like this, let's say the halves that I'm going to divide something like this. For an example, let's say. So if I divide this half, you see this half is not sorted, right? And this half is sorted, right? So that is how we are going to decide, based on one half will be always sorted, another half won't be sorted. So in the sorted half, what we will do, we will check if our target lies in the sorted half or not. Because if a array is given sorted to us, let's say 1 2 3 4 5 like this, and we have to find if this target lies in this half or not, then we can do a simple comparison, right? That this value should be within this two range, right? If it is, then which means it lies here. So we can move our mid value accordingly. If it doesn't, then we have to move our mid value outside. Okay, so that is the approach that we are going to apply. And we know in binary search we have this low pointer, we have this high pointer, and then we have this mid pointer. Okay, so now we will compare this low and mid pointer. If this low value is less than equal to this mid value, in our case it is, which means this is sorted. Since this is sorted, we can definitely check that if our target lies here or not. So 0 don't lies here, so we have to move our low pointer to mid plus 1. Okay, so our no, new low will be here. Okay, and again the new mid will be here. Now we can compare directly with the mid and check if this value is equal or not. Since it is not equal to the target, so we have to again do the comparison. Then again for this low and this mid, we will see if the values are sorted or not. So when we compared this 0 and 1, basically nums of low is less than equal to nums of mid, which means this value is sorted. Now since it is sorted, we can move our we can check if 0 lies here or not. We know when we checked in this particular range, 0 lies here, right? So in that case, what we can do, we can move our high pointer to mid minus 1. Okay, so now we will move our high pointer to mid minus. Mid is pointing here, so our high will point here. Yeah, so this high pointer will be also pointing here, so now new mid will be here. Okay, so this is my new mid. Now if I compare the mid with target, so this is equal to 0, which means we have found our answer. So we'll return 4 for him from here. Okay, so what we did, but at every step, since this was a sorted rotated array, we know that one half will be always sorted. Okay, one will be sorted, another will not be sorted. Okay, so so whenever we find a sorted place, so we can compare if our target lies here or not. Okay, in the sorted half, if it lies, which means our mid pointer will be here, right? So we can move our high pointer to here. Okay, if this is the sorted half, because it lies here. If it doesn't lies here, which means it will be lying somewhere in this unsorted half, right? So in that case, what we can do, we can move our low pointer to here. Okay, so this is just the few things that we have to do. And even after moving, we need to check, okay, if it lies here in this particular range. So one first part was to decide if it is a sorted part or not. If this is the if this is sorted part, then we will check here. If this is not sorted part, then we will check this side. Okay, this is the first check. And second check was if we since we will always go to the sorted part only. Basically we'll explore the sorted part only, so we will check if our answer lies in the sorted part or not. If it lies, then we will explore that part. If not, then we have to find answer in the opposite part. Okay, so that is the core thing that we have to do. Now let's check the code for this. So here n is nums dot size, we have low pointer, high pointer, and we are this is the standard binary search template. Okay, so low is less than equal to high, this mid is low plus high minus low by 2. This is standard thing. Now here we are having this check if nums of mid is equal to target. If we have found our target, then we can directly return this index. Okay, at any point of time. Now uh, here if nums of low is less than equal to nums of mid, so if this is less, which means that this is my left half and it is sorted. Okay, this is my left half and it is sorted. So if it is sorted, then I will explore that part. Okay, if it is not sorted, then I'll explore the other part which is sorted. So if it is sorted, then if target is greater than nums of low and target is less than nums of mid, which means that this is my sorted half which I'm exploring and my target lies within this only. So this is the comparison. Okay, target is greater than equal to nums of low and target is uh, basically within this nums of mid. So then what we need to do, we need to move our high pointer to mid minus 1, because since we were exploring this left half, right, this is left half and this is right half, and we are exploring left half, so our high would be pointing somewhere here, right? So we need to move our high pointer here, right, mid minus 1. So we will do that if our target lies within the sorted half. If it doesn't lies in this sorted half, then we have to explore the remaining half, right? So that we will do. using moving this low pointer to mid minus 1. So our low would be pointing somewhere here. So we need to move our low to mid plus 1. So our new low will be here because our answer don't lie in this left sorted part. We have to explore this part. Okay. So this was the case when our left part was sorted. Okay. If our left part is not sorted, so we can decide our answer from the right sorted part only, right? So this is our right sorted part. Here also we will do the same check. If target is greater than nums of mid and target is less than equal to nums of high. So this was our left part and this was our right half. Okay, left half and right half. And if target is in this range, okay, if target is greater than nums of mid and it is less than equal to nums of high, which means our target lies here. So our low would be pointing here, right? So we can move our low to mid plus 1. Okay, because our answer lies here. If it doesn't lies here, which means it will automatically lie in this half, right? So we can move our high to mid minus 1. Same thing as this if. Okay, so this is the check that we are doing every time we are discarding one half based on the sorted half. Basically in sorted half we can determine if a target lies or not. That is the check that we are doing. Okay, if it is lying in that half, we are reducing our search space. If it is not, then we are exploring the second half. Okay, so that is what it is. And the time complexity, since we are always reducing the another half, so time complexity is nothing but O of log n, which is expected for this question. And space complexity is O of 1, since we are taking just few variables. So yeah, that's about the space and time complexity for this approach. I hope you like this video. Thank you for watching. Stay tuned for next videos.